So, for those listening in the future, it's Semester 2, 2016. It's Maths 1B revision seminar. We're talking about Taylor series. And since I've already got one there on Taylor series, maybe what I'll do is ask you guys what you want me to talk about. You know, any specific questions that are burning in your mind about Taylor series, or general questions, of course. Yep.
Can you talk about finding the error and the remainder?
That seems like a fairly clear thing that people want to know. Okay. Well, let's see. The purpose of a Taylor series is the purpose of a Taylor polynomial is to approximate a function using a polynomial. That's what it's for. And so since it's an approximation, it would be a good idea to know how close your answer is. Interestingly, when we did the bisection method and Newton's method, we didn't talk about how close our answer was. We just sort of kept going, and we didn't talk about anything like that, error formulas for Newton's method. But if you do numerical methods too, you'll talk all about errors for all sorts of things. But in Maths 1B, the only time we see it is with Taylor series. So I'm going to write that down. So the point of a Taylor series / polynomial is to approximate a function. And when we approximate things, we'd like to know how close the answer is. I mean, if we knew exactly how close the answer is, we wouldn't have to approximate it, because we could just add the difference and then that would be the correct answer. So we want to know approximately how close it is. To the real answer. And in fact, what we really want to know is how bad is it? We want to know how bad could our approximation actually be, how far from the real answer it is. So we don't really want to know how close, we want to know how far it is. Okay? Right. And that, how far it is to the real answer, is the remainder. There you go. So there's a little bit of sort of philosophy here that is a little bit hidden that makes this a little more confusing than it needs to be. So the idea is that your function, so given a specific x, fx is the function value. Pnx is the approximation using the Taylor polynomial. And the difference between them is the remainder. So the first piece of philosophy is that the remainder is itself a function of x. Different x's will give you different remainders. This is different for different x, which means it's a function of x. And so, because it's a function, we elevate it by giving it a name of its own. The n is important because it'll be different depending on what n is as well. Okay. The next bit is that Rnx has a proper actual value. There is a value that Rnx has. Okay? Every x, given a specific function and a specific n, every x has a specific value for the remainder. And that's great, and I could draw a graph of the remainder. But the problem is that if I don't know how to calculate f, maybe it's ln x and all I have is a adding machine on my desk like Newton had. Well, if I don't know how to calculate f, then I can't calculate r either. Which is a problem because the whole point of this is to know how big r is. That's a problem. So we are going to figure out how far my approximation is to the real answer, but we're going to have to approximate how far the approximation is to the real answer. That's the big problem. So we don't know the real Rnx. So we have to approximate it as well. Which is sad. But Taylor comes to the rescue with his fabulous theorem. Taylor's theorem tells us how. It doesn't do a particularly good job of telling us how, but it's the best we've got. So Taylor's theorem says that there is a number somewhere between the centre of your Taylor series, like the A that you normally talk about, and the x that you're trying to figure out, such that when you sub it into a specific formula, it will give you the exact correct answer. Only Taylor's theorem doesn't tell you what that number is to sub in. It's still a bit of a problem, but we're closer, okay? So it says that Taylor's theorem, in my own words, says that there is this formula which goes the n plus 1th derivative, and we put something in this space, divided by n plus 1 factorial times x minus the centre of my Taylor series to the n plus 1. There's this formula, right? And there is a number z that I can put here. That goes here. So that the formula comes out to the exact correct remainder. That's Taylor's theorem, in my words. I'll write the official Maths 1B theorem that you would put in your exam if they asked you what Taylor's theorem was. But that's my words. So the formula comes out to the correct answer, and not only that, but wait, z is between the a and the x that I was thinking of. Only it'll be a different z for every x. sadly. Okay, so the version that is in your notes goes the Massey version of Taylor's theorem goes there is a z between a and x such that Rnx is f n plus 1 z over n plus 1 factorial x minus a to the n plus 1. So if anyone ever asks you, what's Taylor's theorem? You'll say, that. I mean, technically you're supposed to say, given that f is a function and Pn is the Taylor polynomial and Rn is the remainder, blah. But that's usually already covered when someone asks you. Right. So notice that this is, notice that this is Taylor's theorem. Taylor series is the infinite, Taylor polynomial is the Pn, Taylor series is the infinite one that goes on forever. Taylor's theorem is all about the remainder. Alright, but unfortunately, again, it's a different z for every x, and the theorem doesn't tell me what z is. It tells me that there is a number that goes in this spot, so it comes out to the correct remainder, but it doesn't tell me what the remainder actually is. And so all the best I can do is look at all the options for what z could be and figure out all the things that the remainder, you know, what this answer comes to for all those different z's and say, well, one of those answers is the correct remainder. If I just pick the biggest one, it can't be any worse than that. Basically, that's the idea. Could be, and pick the biggest. Can't be worse than that. Yep, need to think about all the answers that could be, pick the biggest, and the error can't be any worse than that. And that's basically the deal. So, all right. I'm going to make a point in a second after I sharpen my pencil. So, the problem with remainders is that you can't calculate them from the terms of the Taylor series. So you may calculate your Taylor series, figure out that the nth term is, I don't know, n factorial, 5 on n factorial or something, times x to the n. But you won't be able to figure out what the formula for the remainder is from that information. The only way to figure out the remainder is to go back to the part where you found the derivatives. What's a good function? I don't know. No, I do not want to do that. Let's do that one. It's a classic. Maybe I should have done sine. Doesn't matter. Okay. So what I'm going to do, ultimately, I'm going to get to doing a remainder at a specific point. But I'm just going to do various different options for what could happen at this point. So There's all these different things you can do with the remainder, different questions you could ask about it, and I'll try and do them all in different versions of this. But the first thing we need to do to get to the remainder is to figure out what the n plus 1th derivative of my function is. Okay, so the best way to differentiate this would be to write it as a power, and I'll have minus 1 x plus 2, or maybe I should make it harder. Yeah. Okay, the reason I'm making it harder is so that when you get to the exam it won't seem so bad. So I've got 3x plus 2 to the minus 1. So when I differentiate that, the power will come down and the power will go down by 1. But then because of the chain rule, I'll have to multiply the derivative of what's on the inside. So that's what I get. Maybe I'll just get another step. I am deliberately not simplifying this. I'm just rearranging it so it's in a better order. So the minus 1 and the 3 are constants, so when I do, and they're multiplied on, so when I differentiate them they'll still be there. And then I'll multiply by the current power, and the power will go down by 1, and then I'll have to times by the derivative again. Okay. Minus 1 times minus 2 times 3 times 3. Beautiful. And my third derivative, all of these are numbers and they'll just stay there. But, oh damn it. I'll have to times by the current power. And the power will go down by 1, but because of the chain rule, the 3 will come out. And so I've got okay, this is when I can guess what the nth derivative is. Let's look at all these things. So down here at the third derivative, I have 1 times 2 times 3, I'm going to ignore the minuses for the moment. 1 times 2 times 3, this one's 1 times 2, this one's just 1. And so that would be a factorial. That's what factorial is. 1 times 2 times 3, 1 times 2 times 3 times 4. I've got a factorial there. So the nth derivative is an n fact, only, just a second. Yes, it is this matches that number. Okay, it might be in some of them that it's the fourth derivative that has the 3, and so it would be n minus 1 factorial. And also when I look at this, I've got a minus 1 and another minus 1 and another minus 1, so it's minus 1 to the n. Because I've got 3 minus 1s, and that's the derivative I was up to. And I've got a 3 times 3 times 3, which is 3 to the n. And this number is 1 more than the number I'm up to. And that's where I am. I should just check, for completeness' sake, whether this applies way back at the 0th derivative, because otherwise I'm going to have to tell the reader it only works for n greater than 1 or something. So when I go back to here, can I fit them both on the page? As I can. When n is 0, minus 1 to the 0 is 1, and 0 factorial is 1, 3 to the 0 is 1, minus 0 plus 1 is 1, which gives me that answer. Okay, so it even works when n is 0. Sometimes won't match the 0th derivative or the first derivative, and it'll only start further up, and so you have to calculate those ones separately. Okay. And this is the point at which our paths can diverge. Okay? We can either take one path, which goes towards calculating the nth term of the Taylor series, or we can take another path, which goes towards calculating the remainder term. So I'll do both just so you can compare them. Well, I haven't picked a Taylor series yet. What centre do you want? Do you want it to be a Maclaurin series? Do you want it to be at some other point? What was that? No one cares? Let's do x equals 1. Which by I mean A. There, that's the A I'm talking to. At. About. Talking about. Let's choose the right preposition. So when you pick a centre for your Taylor series, in fact I might just say centre. Okay, so when you pick a centre for your Taylor series, you sub that into your nth derivative. Like that. I'm sure I could simplify that a little. It doesn't look pretty at the moment. How about that? Looks a bit prettier. So that 5 to the n plus 1 is a 5 to the 1 times 5 to the n, because when you add up in the powers it's multiplication down below. That's much better. Well, that's marginally better. Not much better. I could put the negative 1 in there. It's traditional to leave the minus 1 to the n outside by itself to remind the reader that it flip-flops back and forth between plus and minus. But you could put the minus 1 in if you wanted, like in one of the assignments this semester. But yeah, it's traditional to leave the minus 1 to the n all by itself. Okay. And then I need to divide by n factorial and times by x to the n. And in this case, my n factorials magically cancel each other out. It is possible that you'll have an n factorial on the top and an n plus 1 factorial on the bottom, and only most of it will cancel out, leaving an n plus 1 all by itself. So just as a note, maybe you could have an n factorial over n plus 1 factorial. Yep. I totally should have an x minus 1 to the n. Because the centre is 1, isn't it? Beautiful. Thank you. With just an x to the n as a Maclaurin series. Yeah. In which case that would just come out to 1 over n plus 1. And that's because the top is 1 times 2 times all the way up to n. The bottom is 1 times 2 times all the way up to n, and then an extra n plus 1. So everything cancels except the n plus 1. So that's just a side note. So that's the nth term of the Taylor series. Okay, that bit just there. Bang. Not particularly edifying. So that's one thing that we could do using the information of the nth derivative, which was here. The other thing we could do using the information of the nth derivative is find the remainder term. So to find the remainder term, we need to go back to our nth derivative, which was here. And we need to turn it into the n plus 1th derivative. By replacing all the n's with n plus 1. Of course, when I replace this n with an n plus 1, I'll have n plus 1 plus 1, and so it'll be n plus 2. So basically, any term, any piece of it that involves an n or an n plus 1, you've got to bump up by 1. And then I'll sub z into it and divide by, pardon me, divide by n plus 1 factorial, and then put an x minus 1 to the n plus 1. So lots of people will do this step where they put sub the z in one go. Okay, rather than having to write it out twice, I'm just going to do this. Like that. So I'll take what I just figured out, that's not a z, that's a 2. And I'll divide by n plus 1 factorial, and I'll multiply, and I didn't leave room for it. I gave myself so much space, and I didn't even show you what I was writing. And conveniently, again, the n plus 1s cancel out. So that is my remainder term. Oh, did it again, sorry. Despite what it says in your Maple TA, this is not Rnz. It's not a function of z. I mean, we have to consider what it could be for all the different possibilities that z could be, but philosophically there is exactly one z that makes this work. I just don't know what it is. And so it's not a function of z, it's a function of x. Probably no one will notice, but you know, a grumpy marker might be grumpy about it. What I wanted to really point out is that this is a lot different to the nth term of the Taylor series. It has most of the same pieces, but what it doesn't have is these 5s. See these 5s here that are in the nth term of the Taylor series? They're not in the remainder because that 5 came from subbing in a 1. And I haven't subbed in a 1, I subbed in a z. Okay, so there's your diverging paths. We calculated all the derivatives, we used them to guess what the nth derivative is, and from that point forward I can go one way and calculate the nth term of the Taylor series, or I can go another way and calculate the remainder. Right. So here's a question. You know, for this function, what was my function? Doesn't really matter. For this function, find an upper bound for the error in P5 of 1.8. That's a classic question. Now, note it doesn't say remainder. So the remainder could be positive or it could be negative, depending on what the x is, depending on what the n is. But the error is the absolute value of that. It's just the positive thing. So the error so it's minus 1 to the 5 plus 1, 3 to the 5 plus 1, 3z plus 2 to the minus 5 plus 2, 1.8 minus 1 to the 5 plus 1. I'm just subbing it in exactly as it said before. All the n's have become 5 and the x has become a 1.8. And so minus 1 to the 6 is just 1. 3 to the 6 is, I can't be bothered. To the minus 7, and we get 0.8 to the 6. Okay. All right. I suppose I could simplify that a little, just for my own purposes. 3 times 0.8 would be 2.4. Okay. So this is where I am at the moment. That's what the error is for some z. And it's between 1 and 1.8. So some z somewhere between 1 and 1.8 will make that the correct answer for the error. Actually, do you know what? With the absolute value, this wouldn't even be here. Like, I'm going to leave it in. Right. So if I had done it at 0.8, this number would have been minus 0.2, but because of the absolute value, the minus would have disappeared. Okay. So, now it's saying, I need an upper bound for this error. I know that there is a z between 1 and 1.8 that gives me the correct answer for the error, but I don't know what it is. So I've got to go through all the different options for what z could be and pick out of those whichever of them gives me the biggest answer for this. And that's going to be based entirely on just this bit. I'll just put it exactly as it is. 3z plus 2 to the minus 7 is 1 over 3z plus 2 to the 7. And the bigger the denominator is, the smaller that's going to be. So this is larger for smaller. So it's larger for smaller z, and it's smaller for bigger z. Actually, I have a feeling I need to be much more careful than that. It's actually going to be smaller for z's that are closer to minus 2/3. The closer 3z plus 2 is to 0, the bigger this is. Sorry about that. And so we really need to figure out which number in there makes that the closest to 0. And the answer is z equals 1. So basically, if you've got something in the denominator, the closer the denominator is to 0, the bigger their answer is. So we need to make that as close to 0 as we can, and z being 1 will do the trick. So choose z equals 1, and then the error is less than or equal to 2.4 to the 6, 3 times 1 plus 2 to the minus 7, which is whatever it is. (2.4 to the power of 6) divided by 5 to the power of 0.00 0.25. Okay, so we've got better than 2 decimal places. 0.005 would be 2 decimal places. So we've got better than 2 decimal places accuracy with our fifth Taylor polynomial. Okay, another question one could be asked is, for this function, what does n have to be for Pn of 1.8 to be, maybe not better than, at least 4 decimal place accuracy? Well, this time we don't know what n is. So we can say the error is the absolute value of Rn 1.8, which is the absolute value of minus 1 to the n plus 1, 3 to the n plus 1, 3z plus 2 to the minus n plus 2, 1.8 minus 1 to the n plus 1. So this time we know what the x is. It's still 1.8, but we don't know what the n is. And so we're getting, I should have left an absolute value in there before, I'm sorry. So we've got the same situation happening, but it's an n plus. Okay, that's where we're up to. Now the same reasoning that worked before will tell us that the maximum will happen when z is, the maximum possible answer for what happens when you put the z's in is it happens when z is 1. So same argument as before says, that's an A, that the error is less than or equal to 2.4 is, oh no, I won't put the 5 in, I'll just be really clear that I'd put a 1 in for that. Like that. This is where it would actually be quite useful to figure out, to try and lump this together somehow. So if I take one of those 5s off, I'm going to get that. So what I did is I separated the n plus 1 and a 1 to give me an n plus 1 times 5. And then because both of these have an n plus 1 power, I brought that inside the brackets. And 2.4 divided by 5 would be 0.48. And that's where I am so far. Now the question actually said, I want it to be at least 4 decimal place accuracy. Now that means I want the error to be less than 0.0005. 4 decimal place accuracy. 1, 2, 3, 4. And then a 5. Because then it will still round off to the right answer. Or is it the next one after that? That's all right, we haven't changed the first decimal place. We haven't changed the first 4 decimal places, and the next one is changing by less than 5. Yep, it'll work. So 4 decimal place accuracy has 4 zeros after the decimal place and a 5, which is 5 to the minus 5. 5 times 10 to the minus 5. And the only way that we can guarantee that the error is less than this is for this number to be less than that. Technically, we don't really know. We've got error is less than something and error is less than something. We don't really know what order those three numbers are in. But if we make sure that this is less than 0.05, then the error will have to be less than several zeros 5. So at this point, you may want to try trial and error. If you had a factorial in your answer, you would need trial and error, and I may possibly, depending on how much time I've got, I might possibly do a bit of a what if there. But at this stage, I can actually do this one accurately using logs. So I've got 10. If I do ln on both sides, then doing ln means the power can come down. Now I'm just going to divide both sides by ln of 0.48. And here's where a special trick happened. ln of 0.48 is negative because 0.48 is less than 1, and so ln of anything less than 1 will be negative, so my inequality sign is going to switch over. Because I divided by ln of 0.48, which is negative. And so my n is going to be whatever that answer is. Let's see. ln of 0.12325 divided by ln of 0.48 minus 1. So n is greater than 10.3, so choose n equals 11. Always round up, because you don't know if it's going to work at 10.3, which means you don't know if it's going to work at 10, so you go up to the next one. All right, feel free to go if you need to. But I did just want to do a what if for the recording.
Solids rotation solids thing, is that?
Oh yeah, I should say on the website you'll see solids of rotation. If you click on that, it will say that's no longer in the curriculum, but I need it there because some people in later years have to know how to do it even though it's not in Maths 1B, so I leave it there so that I can direct them to it.
Yeah,
that's why it's there.
The 2013 exam,
Yeah.
I don't know how to do this.
Solids of rotation is no longer in the course. Okay. I'll just wait a couple of seconds. What if it hadn't been as simple as just being a single power, something to the n, and it had like an n or something involved in it? Well, in that case, you're going to have to do a bit of trial and error. A not bad plan is to try doing it ignoring that the n is there and figure out what number that was using logs and then adjust it afterwards. Okay, so the thing is that without the n, this number's small. With the n, this number's smaller because we're dividing by something. So what I'm going to do is I'm going to say I'll try it without the n. And then that, using the working that I got before, I ended up with n equals, I'll keep the fifth in there. I'll end up with n equals 11, okay? But then I know that because, since dividing by n makes it smaller, I'll get to that level of that small number earlier because I'm using smaller numbers here. This number is smaller than the number I was going for, so what I'll do is I'll start going down from there. I'll go n equals 10, and I'll figure out what the error is for that. N equals 10. 1/5 of 0.48 to the 11 over 10 is 1, 2, 3, 4, 5, 6. And so I'll keep trying. I might even skip a couple because that's really quite small. Let's try it with 8. So I'm getting there. It looks like it probably would have just been quicker to start at 1 and try them all, but whatever. That's my normal strategy. Let's try the next one. So when we went down by 2, we only lost 1, 2, 3, 4, 5. It was 6 before, wasn't it? 6. We went down by 5. So going down by 2 lost one of these zeros, so I reckon we should go down by... How many zeros did we need? 1, 2, 3. So that'd be like 2. I'll try 3, see what we get. Not small enough, my friends. Damn it. So trial and error. Yep. Oh, so I don't need the fifth, do I? You're right. All the same, that doesn't make any difference to the question, does it? I can leave that out, you're saying? Yep, I gotcha. You're right, the 0.025 came from the 1/5. All right. That just serves me right for making stuff up on the spot, really. It's one of the reasons why your lecturers prepare better. So when we had 10, I'm just going to fix that. And when we had 8, it was 1, 2, 3, 1. Actually, so it looks like 9 is the go. because we need 1, 2, 3, 4 and a 2. So I'll try 9 and see what I get. Sorry? 0.0001. That's what I'm getting. Oh, I could have that wrong, but that's okay. So this one's good, but this one isn't. So we need n equals 9. Yep.
Would we be expected to solve something like that or just go through it with like trial and error?
You could go through it with trial and error. If I had done it right to begin with, it would only have taken me 3 tries, right?
Would we get a question that involves like an experiment and then a...
Probably it might. But the thing is that you don't normally have to show all that working. Like, because if I was going to do this on an exam, the only thing I would have shown is that one and that one. Like all I would have shown is the trial and error part, and I probably wouldn't have even written this down. I'd just write error equals. So, to be fair, you could probably get away with just putting the answer, but you'd maybe at least put the n equals 9 and then show what the error is, so that you can see that it's less than it's supposed to be. But this little squiggly bit here, you can quickly scribble on your scrap paper and do a guess. But all the same, in the end, most of the time you can just go, I don't know, just going to guess. Just going to guess. What a lot of lecturers will do will say, well, this is sort of in the order of, it's like about a half. And that 0.48 is about a half. And so as I go down to like 10 times, it'll be 1,000th, which is 0.001. So 10 is not the worst answer. So you just make a quick guess. And then you'll try it and see what you get. So, yeah. In the end, well, you'll get what you get. And you can at least, in exam situations, what you can do, you can say, this is what we need. And there's only going to be like 1 mark for the actual final answer. So you can skip it if you don't have time. Of course, you can't do that to too many things. So the more 1 marks you lose, the less marks you have. Thank you very much. I'm going to stop there. Please don't forget there's all these other revision seminars, and the Maths Learning Centre is open tomorrow and the next day.